Hello everyone, this is Fedor Liang from ARM Trusted Firmware for Cortex-M team. Today, I will give a presentation about full-point support in Trusted Firmware for Cortex-M. Two parts will be introduced today. The first is introduction about full-point unit, which is sometimes abbreviated as FPU. And the second is full-point support in Trusted Firmware for Cortex-M. Although many applications can be implemented using integer, there are still high demand to process with float-point numbers because float-point data allows the processor to handle a much wider data range as well as very small values compared to the integers or fixed-point data. FPU is the hardware unit integrated in the processor which can be used to accelerate the calculations of float-point numbers. With FPU, float-point operations are entirely done by hardware only in several cycles for most of the instructions. ARM FPU architecture provides high performance and high efficiency hardware support for float-pointing operation, which is fully IEEE 754 compliant. The FPU is optional in several Cortex-M processors. This presentation is based on ARM v8 architecture and later for FP support on Cortex-M processors. FPU adds several registers to the processor. The first is coprocessor access control register, which can be used to specify whether you can enable or disable FPU. Then is the FP register bank, which consists of 32 registers S0 to S31. And from S0 to S15 is the FP color sealed registers, and the X16 to X31 is FP core E sealed registers. Also, coprocessor power control register for power control of the coprocessor. For other registers, please check the spec for more information. In order to process full-point calculation, there are three different application binary interface arrangements to specify how the parameter and results passing between the core and core E. The first ABI option is software FP option. All the full-point operations are handled by runtime library functions, and the values are passed via the integer register bank. And the second option is hybrid FP option. This allows the compile code to directly access FPU, but still using the integer register bank for parameter and result. And the third FP option is hardware option. This allows the code to directly access FPU and use FP register bank during function call. As we know, if FP context is active in current thread, the FP registers will be saved and restored during exception return automatically by the hardware. In order to minimizing the exception latency, ARM introduced the lazy stacking mechanism to improve the performance of exception. During exception entry, the processor will only reserve extra space in the stack frame for the FP registers. However, the active stacking of those registers doesn't take place. If exception handler doesn't use FPU during the exception return, unstacking of those FP registers is ignored. If exception handler uses FPU at some stage, the processor is stored when the first FP instruction takes place, while FP registers are pushed to the stack at the address which is stored in the full-point context address register. And during exception return, unstacking those FP registers accordingly. Security aspect of device can be addressed by both hardware and software side. ARM TrustZone technology offers an efficient system-wide approach to security with hardware-enforced isolation built into the processor. Trusted Firmware for Cortex-M is reference security firmware for Cortex-M-based processor support TrustZone. Trusted Firmware for Cortex-M can be abbreviated as TFM. Now let's talk about how to enable and disable FPU. There are three resistors. The first is coprocessor power control resistor, and the second is non-secure access control resistor, and the third is coprocessor access control resistor. Depends on the FPU usage in the system. If FPU is only used by the non-secure side, so the secure software need to configure the non-secure access control resistor first, then the non-secure software will configure the coprocessor access control resistor. If FPU is used by the secure side only, the secure software need to configure the coprocessor power control resistor to prevent non-secure side from modifying FPU's power supply, and then configure the coprocessor access control resistor. If FPU is used by the non-secure side and secure side both, so the secure software need to configure the non-secure access control resistor and coprocessor access control resistor. Then the non-secure software will control the coprocessor access control resistor from the non-secure side. A processor with TrustZone support has non-secure and secure states which are orthogonal to the traditional thread and handler mode. For secure side, TFM is divided into several partitions and into secure partition manager. The several secure partitions running and each has a thread for providing the secure service for non-secure and secure side. The P root partition is the root of trust of the whole system, and the application root partitions provide the security service to the system. SPM runs in the handler mode to do scheduler for those secure threads and configure secure isolation for threads by secure MPU. Since different products have different security needs, there are three levels of isolation. The first isolation level 1 separates the secure and non-secure side. The isolation level 2 separates the P root and A root partition class. For the isolation level 3, separate the secure partitions class. So we could get the objective for different isolation level. For isolation level 1, protect FP context in secure partition before switch to the non-secure side. For isolation level 2, has the same objective of isolation level 1 plus protect FP context in P root partition. For isolation level 3, it has the same objective as isolation level 2 plus protect FP context in A root and P root partition. This is the software routine in TFM. In the picture, the upper is secure word and the bottom is non-secure word. The processor starts up from reset in secure state, then boot up from the secure partition manager initialization. Once secure software is up and running, the software branches to non-secure side, then the non-secure starts for its initialization. After the whole system has started up, non-secure software access the virus security service provided by the secure application by the secure API. Now let's do some analysis about the risk of FP context leakage in TFM. After the whole system has started up, security state transition happens for the following scenario. First is non-secure application call secure API and return to the non-secure world, shown as number 1 and number 2. The second is secure function call a non-secure function and return to the secure world, shown as number 3 and number 4. Then the non-secure exception occurs during the secure thread execution, shown as number 7 and number 8. Then the secure exception occurs during the execution of the non-secure thread, shown as number 9 and number 10. Also, there is the running for the secure partition manager for scheduling of the secure thread, shown as 11, 12, 13 in the picture. So we can get the risk for secure FP context leakage differs on different isolation level. For isolation level 1, the risk happens when data transition from secure to the non-secure side, which has 3 scenarios. First is function call or function return to the non-secure side is number 2 and number 3 in the picture. The second is non-secure exception entry during the secure thread, which shows as number 7. Also, the secure exception return to the non-secure thread, which is number 9 in the picture. And for isolation level 2 and level 3, the risk of FP context leakage is inside the SPM, shown as 11, 12, 13 in the picture. After we do the analysis of the risk of FP context leakage, let's see what kind of FP context should be protected. Here are the registers listed. We can see that for the FP register bank and FP status and control register is not banked between the security states. So these 2 registers should be protected. Also for the lazy stacking enabled case, for isolation level 2 and level 3, the FP context address register should also be protected. All these FP contexts should be cleared before security state change. It depends on the isolation level. Here is some guidelines for the FP support in TFM. The first guideline is that we have to make sure that non-secure exceptions are deprioritized. This makes sure that the secure exception cannot be interrupted by the non-secure exception. Also, there is no tail chaining between the secure and non-secure exception handler. The second guideline is that SPM doesn't touch full point operation, but partitions may do so. So no side effect caused by the SPM itself. The second guideline is that in TFM is that all the secure API is a supervisor call, which means secure PIC call cannot be interrupted by the non-fault exceptions. Since all the secure APIs in TFM is a supervisor call, there is a special case for enabling FPU. We will talk this later. If FPU is used by non-secure side only and the lazy stacking is disabled, we should enable FPU on the secure side either. The reason is that all the secure API in TFM is a supervisor call. If non-secure thread call secure API with FP context active, after enter secure side, during the SVC call in SPM, the processor perceives FP context belonging to the non-secure side to its stack at SVC exception entry. If FPU is not enabled on the secure side, fault generated. The secure and the non-secure software do interaction using function call as we had discussed before in the data flow in TFM. ARM has introduced a range of C compiler support features called the Cortex-M Security Extension, CMSC. The function called with the CMSC feature will prevent secure information leakage. The compiler will generate a code sequence which ensures that secure data inside the read bank will be erased before return to the non-secure world, except the result returned. Now let's look at how to protect FP context in partition for isolation level 2 and level 3. There are two scenarios. The first is for lazy stacking disabled. The FP context will be saved and restored by the hardware during PendSV exception. PendSV exception is used as a scheduler in TFM for the secure side. There is no risk for FP context leakage for this scenario. If lazy stacking is enabled, we should protect the FP context in thread in the SPM scheduler. Let's talk this more detail. In SPM scheduler, FP context should be saved to current thread stack and cleared before switch to another thread for isolation 2 and isolation 3. And those FP contexts will be restored when the thread swept in during PendSV exception return. If lazy stacking enabled during the PendSV entry in the secure scheduler, PendSV only reserves space for the FP register on current thread stack memory. Then check whether FPU is used in the current thread. If FP context is active, just trigger the lazy stacking by one simple FP instruction. Then CPU is stored and FP registers are stacked on current thread memory. For isolation level 1, all the secure partitions are in the same secure zone, but FP context still need to be sealed, but not need to cleared to prevent data corruption in thread. At the same time, for isolation level 2 and level 3, full point context address, the register should be cleared before context switch to another thread to prevent the FP context of current thread is tampered by the other thread. And during the PendSV return in the scheduler, FP registers are restored by the hardware automatically from the thread swept in, from the swept in thread map. Now let's talk about how to protect FP context during the non-secure except entry when the secure thread running. We should enable the option treat full point register as secure. Enable this feature on. This will protect FP context in secure thread when interrupted by the non-secure exception. We can see that besides the FP caller register, FP call E register is also stacked during the non-secure exception entry. Another case is to protect the secure FP context during the secure exception return. We should enable the option of clear float point caller sealed register on exception return. Together with the previous treat float point register as a secure option, these two options can protect FP context during the secure exception return to the non-secure thread. As a reminder here, all the compilers need to be upgraded to mitigate the latest vulnerability in FPU on ARM Cortex-M processor. Please check the link below for more information. Okay, that's all for my presentation about full-point support in trusted firmware for Cortex-M. Thank you. Any questions?